All right, thank you very much for having us. So this is a joint project that we did where we attempted some measurements of DNSSEC stuff with post-quantum signature schemes and looked at how it went. And we published that at the ITF, I think in Vancouver in July, and then Ripe was kind enough to ask us if we repeat it here. So here we are, and there's actually also some new additions from Jason's work, so I'll show you all of that later. Okay. So I suppose everyone's aware quantum computers might be a thing, and if they are a thing, they will break current encryption and public key signing schemes. That also affects DNSSEC. Now, I assume everybody knows what DNS is. I don't know how familiar everybody is with DNSSEC. It's just a method of adding signatures to DNS records and then having the recipient or resolver validate them so that it's harder to tamper with stuff in transit. And there's usual devils in the detail, but that's essentially what it is. And it uses public key cryptography, and that's why it's also affected by the post-quantum transition. TCP-based, usually at least. And it's not too difficult to put new signature schemes in there, or encryption schemes rather. In the DNS, stuff is more constrained. It's sometimes very old devices. It's UDP mostly. Weird network setups that are quite historic sometimes. So the situation is a little more complicated. And still we need to secure the DNSSEC world also against potential quantum computing stuff in the future, and that's why we figured let's look at it. Ideally, it would just be drop-in replacements for the current signing schemes, and we'll see if that would be viable or not. NIST is the American, I think, National Institute of Standards and Technology or something like that. And they have looked at the problem also, and there's mainly three candidates, which are called Dilithium, Falcon, and Sphinx, at least casually, and then they have acronyms. And so we particularly looked at those, and I'll tell you more. Okay. So for DNSSEC specifically, I just mentioned that there are size constraints in the DNS because it's UDP. UDP can have large packets, but they can be abused because the source IP address is not easily verified. So you can send fake packets and have DNS questions seemingly come from somewhere, and then that seeming querier gets the response. And if that response is very big, you can drown them in too much traffic, and that's why in the DNS, practically, the package size is limited. So that's a problem if the signatures or keys are very large, and that's what people expect for the post-quantum stuff to be one concern. Concern is if those things are very large, perhaps one could split key queries up into several questions, for example, and then each answer would be as small as before. But then that looks very unusual, at least to legacy middle box things like your home router or something, and then often stuff gets dropped. At least that's the concern. So there's all kinds of implications that become very complicated in detail if you just drop in post-quantum signatures into the DNS world. It might work and it might not work. And we wanted to figure out how often does it work or not work. Then independently of those overall considerations, there's also stuff that applies per algorithm. For example, each algorithm has a certain amount of time it needs for a key pair generation or for signing one record or for validating that. And it's, for example, not very useful if signing takes like 3 hours, right? Okay, so all of that needs to be considered. There's a research agenda that explains the problem space. It's linked here. And yeah, so this is essentially the main points of it. Okay, so I will not go too much into detail about this table of potential algorithms. I just put it here because the reference at the bottom of it is a nice paper explaining the problem space of retrofitting post-quantum cryptography into existing internet protocols. And it has also the three algorithms that I mentioned. There's Crystal Dilithium at the top, that's one I mentioned. There's Falcon, and then there's Sphinx. And those are the three algorithms in this candidate table that have keys and signatures that are all below 10 kilobyte. So they are larger than the conventional ones, but they're not crazily large. So that's why we considered those specifically. We also considered XMSS because it's a different type of signing scheme. It's stateful. And just recently, Jason did experiments with Merkle tree-based stuff that he'll tell you about later. That's also new, I think, just last week. Press. Okay. So in 2022, we started doing this as a small local experiment, no public internet-wide measurements, just in a Docker setup. We used PowerDNS, and we did implement the Falcon signing scheme and validation and published a blog article about it. And things kind of reasonably went well. And we thought maybe we should redo this experiment, not only with PowerDNS, but also with other software. So we used PowerDNS and Bind. And not only do it locally and, you know, kind of unrealistic local network measurements, maybe also do stuff using, for example, the RIPE Atlas network, which has about 10,000 probes, and you can do DNS queries from all of those locations and see how they come out and whether you actually get a response or you don't if those signatures are in place. And we did all kinds of other parameterizations. For example, we tried UDP, TCP queries. We tried including the DNSSEC OK bit in the query, which causes the signatures to be delivered to the client actually, and not just validated by the resolver. So this will increase the packet size on the last mile, which is why it's an interesting thing to try. And also DNSSEC responses differ in size significantly depending on whether the name that you ask for exists or doesn't exist. If it doesn't exist, you get an NX domain response plus the corresponding signatures, and those are larger than the signatures for existing names. So we also tried that, and there is various variations of it. And then you see this KSK, ZSK, and CSK distinction. I'll not get into details, but essentially there is a way of using 2 keys per domain or 1 key for a domain. And so the split case, the first case is the KSK, ZSK. That's what we did with Bind. And for PowerDNS, we did the other case. And we did both because both are used in the actual world. And so we implemented this in Bind and PowerDNS as the authoritative name servers, and also in the corresponding Bind and PowerDNS resolvers, so that we could, well, those are not really on the, like nobody uses our resolvers, obviously, but at least we could show that validation is feasible to implement. Implementation was done with liboqs. That's kind of an OpenSSL spin-off for post-quantum stuff. And here's some technical details. We used RIPE Atlas, as I mentioned before, and did the main study that did not include the Merkle tree stuff yet. In May this year, it was about 2 million queries, I think. And we used zones that we deployed in public and signed with these algorithms. And of course, public resolvers usually would not be able to validate the responses because they don't know how to interpret those signatures, but they should at least not get confused. We then recorded the return code, which is called R code. So for a successful response, for a name that exists, that would be no error response. Or for an inexisting name, it would be NX domain. When there is a refusal somewhere along the resolution chain, it would be refused. Maybe you've seen it before. And then there's also serve fail for other kinds of failures. And so we recorded that. Then depending on whether that return value actually was what we expected it to be, we also recorded whether that was correct or not. So there's a correctness thing. We also recorded whether the response contained the AD bit, that means authenticated data, and it must only be set if the resolver actually validated the response, which we expected for none of the post-quantum responses because obviously nobody supports it yet. And we also recorded response time. Then from that big data set, we excluded a few things from analysis. In particular, we excluded resolvers that do not correctly support conventional DNSSEC, because I think the interesting question is how do we transition conventional DNSSEC to modern or future post-quantum DNSSEC? The question is not how to support post-quantum stuff in deployments that don't have DNSSEC today. We also exclude private IP address ranges like 192, 168, whatever kind of resolvers. That's because we wanted to do UDP and TCP comparison, but it doesn't work on TCP in the DNS query stack for RIPE Atlas. So for consistency, we excluded it also for UDP. And we also excluded network errors and timeouts, which, however, would be interesting to look into the reasons for. But we were mainly concerned with the correctness of the responses we got. Now, this is raw results. I'm not going to talk about any of those numbers, but what's interesting is that you see, for example, in the graph at the top right, which is a UDP graph that asks for DNSSEC signatures with this DNSSEC OK bit, that in various columns, which are the response codes, there's various colors and various rows, and those correspond to the algorithms. And you can see at the top there is green stuff, which is conventional DNSSEC, and then it gets more blue, and the more to the bottom you go, the worse it gets, kind of, right? And that correlates with the success rates. And then we looked at this, looking at where are interesting spots, and then we zoomed into those. So this is a zoom into responses for queries with a valid question name that did exist, for example, ripe.net. I mean, we didn't have that zone, but it's a name that exists. And on the left-hand side, you can see the percentage of correct responses without asking for the signatures specifically, just doing a regular DNS resolution. On the right-hand side, the same thing if you do ask for the DNSSEC signatures. And there's two lines for UDP and TCP, and on the right-hand axis is the algorithms. So you can see unsigned and RSA, which is the current stuff, always works. I mean, it was our pre-filter, right? And then you can also see that for Falcon, for example, success rates through UDP and TCP are both very close to 100%. It gets worse if you use dilithium, which has larger, I keep confusing it, keys or signatures. Anyway, larger responses, so the delivery success rates go down, and it gets worse and worse as you go to even larger packets, which is more or less what the algorithm axis correlates with. And on the right-hand side specifically, when you ask for the DNSSEC signatures also, you can see that over UDP, success rates are much lower than over TCP because the message size constraint that I mentioned earlier kicks in. The takeaway from this plot here is that Falcon looks pretty good, actually. Then here's a similar thing for non-existing labels where we expected NX domain responses. It's essentially the same kind of thing, except that there's twice as many values on the x-axis because there is two ways of doing a non-existence proof. One is called NSEC, the other is called NSEC3. So in both plots, you can see two chunks. The left-hand big chunk is with the one method, and then the right-hand chunk is with the other method. You can see that the left-hand chunk kind of looks like the previous slide I showed, and the right-hand one, which is NSEC3, looks even worse. For example, XMSS, which is at the very right, has below 50% success rate, which is because the message size exceeds 64 kilobytes, which is a hard limit for DNS messages. So anyway, it looks like there are combinations, or might be combinations, where one could engineer things such that they work. So the transition, the transmission issues were real. I just explained Falcon leads, and with NSEC3 it's worse than with NSEC and all of that. Overall, if you use just one key and not two, which is the CSK scenario, then things are a little better. 80% success on average, not 70. And if you use TCP, things go better by about 10% also. That's if you don't ask for the signatures. If you do ask for signatures, things go down to roughly 50% because responses are much larger. Interestingly, also about 9% of probe resolver combinations claimed by setting the AD bit in the response that they did verify the signature, which confused us a lot because we don't think anyone validates our signatures. So it's clear that there is bugs in the deployed resolver base. And this is almost my final plot before we go to Merkle stuff, which is a really interesting optimization to get rid of those size constraints. Before we get there, here's a plot of power DNS timing benchmarks for the various algorithms. At the top is RSA and ECDSA, the red and green, which is the current conventional DNSSEC, and Edwards curves, which is the dark blue. And the columns have the time for key pair creation, for signing, and for validation. Note that the x-axis is logarithmic, so each square is a factor of 10 in time. You can see, if you compare to green and red, for example, which is RSA, that the algorithms at the bottom mostly are in the same area. So for example, key generation for Falcon and dilithium is faster than it is for RSA, and the same is true for signing. For validation, I think RSA is a little faster, but dilithium and Falcon roughly compare, for example, with elliptic curves, which is the upper green. So that's not too bad. What's really bad, however, is XMSS key pair generation, which you can see at the very bottom on the left, which is 2 squares out from the others. So it's a factor of 100 slower, and it takes several seconds to generate keys. Now, if you have dynamic deployments of stuff, that's not really practical. Okay, I guess if there's questions, we can go into more details. We also have a public deployment of our stuff. So I mentioned before we have the authoritative zones on authoritative name servers and also the corresponding resolvers. For example, our bind 9 resolver is on bind9.pqdnssec.de.io on port 5304. And you can make queries there for our zones, for example, the dilithium signed zone here. And you will get response, for example, here for an A record, which has an RRSIG DNSSEC signature with algorithm 18, which is the dilithium number we assigned. And it has an AD bit set in the flags at the top, the green thing, because our resolver implements that. You can try this out yourself on this website, pqdnssec.de.io. It's a JavaScript interface with DNS over HTTPS, so you don't even need to open a terminal. And if you scroll down on that page, there is more documentation, raw data, and stuff like that. Yeah, so post-quantum is the future, and maybe the future of the future is Merkle trees. So I'll give it to Jason.
Thank you. So based on our initial findings that Peter just discussed, the big takeaway is we want to use PQC because we don't want our cryptography to be broken, but we need messages to be smaller. And one idea we had was maybe we could use these things called Merkle trees to compress zones. So very briefly, what is a Merkle tree? It's a cryptographic binary tree that lets you associate data together. So in this case, all of your leaf nodes will be hashes of some data, and all of your intermediate nodes are hashes of its child hashes, more or less. So very, very quickly, if we wanted to validate that the bottom left child node belongs to this tree, we would first hash the data. We would then be given H2, combine those two hashes, hash them. We would then be given H6, take both those hashes, combine them, and then hash. And then we would compare against H7, which is our root hash. If they match, then you're good. If they don't, then someone's lying to you and you probably shouldn't trust this, this data. So can we apply this to DNS? Probably, sure. What we can do is, if you'll recall, there were these two keys as an option in DNSSEC. One was the KSK, or the key signing key. What we would do is we would use a standardized DNSSEC algorithm, whether it's PQC, or I guess in this context, we would want to use something PQC. And that would provide us with our authenticity, aka did this come from the person we expected it to come from, and then it would also provide us with integrity. Then we would take the root hash of a Merkle tree that we've constructed, and we would put that in our zone signing key, our data, and that would get signed by our key signing key. So normally Merkle trees just give you integrity, but because we have the root hash signed by a digital signature scheme, it kind of gets upgraded to have the authenticity property as well. And then our signatures become this authentication path, or those sibling hashes, more or less, which is really, really nice because your signature length, it grows logarithmically with how many things you want in the Merkle tree. So in this case, the RR sets. And then there's also this really nice finding that some colleagues of mine at Sandbox found, is that you can reduce hash sizes in half when you're using Merkle trees and still maintain the same level of security. Because in the security model, you can get away with only needing the second pre-image resistance. If you want more info on that, I recommend checking out the publication there. We do need to make some changes to DNS in order for this to work. Namely, we have this circular signing issue. Every time you add something to a Merkle tree, the root node will change. So that will mean that your ZSK will change, and then every time your ZSK would change, your key tag changes, which will then affect what you provide as input to your signing and verifying functions. So that means that we cannot, well, normally you would have your zone signing key also sign your DNS key sets, but we have to make an exception here, because if you were to try to sign the DNS key set with a Merkle tree, it would then change the tree and it's a nightmare. It would just continue to infinity and never work. The other exception we had to make is normally you pass the key tag into your sign and verify function. For Merkle trees, that's also not possible. So in our experience, we just zeroed out that field just for Merkle trees, though. We're not saying get rid of it for everything. So we get two nice wins by doing this. First, this is a plot of DNS messages signed by these algorithms for A records. You'll see the classical crypto all on the left there. ECDSA and RSA are quite small. Falcon's okay. And then dilithium 2, Sphinx, and XMSS they blow up in size. And the red line is what we can fit inside of one MTU without having fragmentation, or the average MTU. So we want to stay below that line as much as possible. When you use a Merkle tree applied to these PQC algorithms, you'll see they both stay below that line, which is quite nice. We also get much cheaper bandwidth zone transfers because there's nothing private involved with building Merkle trees. So you can essentially send these dummy signatures that are very, very small, and then once it's received out of the secondary name server, it can rebuild the tree, make sure the root node matches what's in the ZSK, and then if it does, then you're good to go. So there's a nice trade-off between bandwidth and computation there. We don't have an implementation for that at the moment. So what happened when we used RIPE Atlas? Well, those of you that have a good memory for numbers will notice that Falcon, surprisingly, behaved way worse. We have changed nothing in our testing setup. It's just a time difference. So between May and last week, Falcon has started failing 40% times more. We thought it maybe be like a resource issue, but we upgraded the machine to be well overkill. So we're still investigating that. If anyone has any ideas of what might have caused this sudden drop in success, please come and speak to us. Maybe it might be something weird with our cloud provider, I'm not sure. But the nice thing is you'll see that dilithium still fails quite a bit, similar to the IETF results. But when you apply a Merkle tree to it, it upgrades the success rate to match that of Merkle Falcon and stock Falcon. So even though we have these much larger signatures and keys with dilithium 2, when you apply Merkle tree to it, it succeeds a lot more. So the hypothesis is once we figure out what this weird Falcon issue is, that it would upgrade it to that closer to 100% once Falcon reaches 100% as well. But that's just a theory. We don't have any concrete evidence of that just yet. And it's more or less the same story with non-existent labels. We did have to change how we sign things a little bit. It's worth mentioning. I'll be very brief on this. So instead of just iterating all over your R sets once, you now have to iterate over them all to add them to the tree. Then you have to iterate them all over again to get your authenticating path and get your final root node hash. But the nice thing is, even though we're iterating over it a lot more, it still took about half the time to sign the zone file with about 1 million RR SIGs than it did with ECDSA. So that's still nice. So the kind of big takeaways are, there are some, if you were to use Merkle trees, there would need to be some changes to the DNSSEC protocol. But if you define it as its own algorithm ID, you can hot swap it with any other DNSSEC algorithm instead of having to define a new like Merkle Falcon or Merkle dilithium algorithm ID for every new pair you want to do. So that's kind of nice. Zone updates are a bit limited as well. It would be limited by the time to live of the ZSK. But there's some work by VeriSign called Merkle Tree Ladders that they really like talking about. So if you see anyone from VeriSign, talk to them about it, I'm sure. They'd love to talk about it. That might resolve that. It's also worth mentioning that the actual DNS key query doesn't get compressed. It's just, it'll just be for any of your other queries. And we did see an improvement in deliverability of these large signature zones. And it's also worth mentioning, unlike stateful hash-based signatures, which tend to use Merkle trees under the hood, you don't have to maintain a central secret state because there's nothing secret about Merkle trees themselves. Everything can be public without losing any security. So the biggest takeaway, if you listen to this presentation, is that transitioning to PQC will be non-trivial. This is just an example of one protocol where it will be non-trivial, but it will be non-trivial in general. So we need to start planning now. And now you have 20 seconds to cover this.
Okay. Yeah, I guess we essentially said what we wanted to say, right? I mean, some stuff needs to change. We'll need to see how it looks in the future, or it might look. There's other ideas like other fragmentation ideas like ARRF. I'll not go into it. Right. One thing to remember is if we don't take DNSSEC automation into account, updating the DS records in the parent that link the keys into the child, even the best PQC solution probably won't help very much because all the domain owners would manually have to do the change. So I think to make this a success and not have DNSSEC fail, even though there is a solution for PQC, we also need to manage automated transitions. Yeah, so overall future work is needed. There is a mailing list at the IETF, pqdnssec@ietf.org. In Dublin next week, we'll have a side meeting on that on Thursday. So if anyone would like to come to, that's cool. And yeah, I guess we'll open up for questions.